Hello again and welcome. This will be part 5 where I'm looking at the Fluke 87V. Today we're going to be continuing with our transient testing. I've already applied the very first transient, which was at 1000 volts. You can see I have my little pill dispenser out right now. On the right I've got my Bob 199s. Of course that's what the Fluke 87 uses. You can also see I've got our high voltage probe out. Scope should be warmed up. We're going to start off our testing today at 1.5 kV. That just so happens to be the level that the last meter I tested failed at. So let's see if this meter can survive this transient. Let me go ahead and get the transient generator set up and we'll get started. Alright, so you can see we're still at 500 volts per division. And again we're at 100 microseconds per division. You can see we're now 3 divisions up, or 1500 volts. The full width half height again is roughly 100 microseconds. Again, this transient generator has a 2 ohm source impedance. It can output roughly 20 joules at most. Again, these are not safety tests. I'm really interested in how robust the meters are compared to one another. Again, we'll be applying 5 transients, both positive and negative, with each mode of the meter, and then we'll do a functional test on it. Again, this is where the last 87V had failed. I'm hoping that this one can actually survive this test. Let's go ahead. Alright, let's do a real quick check. And this should be roughly 500 degrees Celsius. You can see it's about 20 millivolts. I turn it up, it should be about 40. This will be a 100 ohm resistor. Let's just try it at 100K. This will be 10 meg. This will be a 1 gig ohm resistor, so it should read roughly 1 nanosiemen. This will be 0.1 microfarad. Let's try Diode Check. And that looks fine as well. So the meter looks okay. Let me go ahead and finish functional testing it. Okay, the Fluke 87 passed that test just fine. You can see we're still at 500 volts per division and 100 microseconds per division. You can see we're now 4 divisions up, or 2 kV, and again 100 microsecond full width half height. Again, just like before, we'll be applying 5 transients, both positive and negative, with each mode of the meter, followed by a functional test. Here we go. Okay, that's 2000 volts, or 500 volts higher than what the previous one had failed at. Again, let's just have a look. So far it's hanging in there pretty good. Again, this should be roughly 40 millivolts. Looks good. And this should be roughly 500 degrees. Let's try it with our 10 meg. Looks good. There's a 50 ohm. That looks fine too. Let's try it in capacitance. Again, this will be our 0.1 microfarad. That looks good. Let's try continuity test. And Diode Check. Alright, I'll go ahead and finish functional testing it, but it looks like it survived. Alright, so our 87V passed the functional test. You can see we're still at 500 volts per division and 100 microseconds. We are now 5 divisions up, or 2.5 kV with 100 microsecond full width half height. And that would be roughly right here. I would say the fact that the meter has survived this far means that they've made some change possibly to the meter. Again, I think the previous meter I looked at had a revision of 10 maybe for the circuit board. I know that meter still had the GSM problem, and we know there's another change obviously with the hardware, because now when we put the meter into high Z mode and I remove an overload condition, the meter clears out instantly. It didn't used to do that. So something has changed about the meter, I don't know what. I would say it's definitely more robust now. The question is, how robust? So here we go. This will be 2.5 kV, again 5 transients. This will be a 2 ohm source impedance. I tell you, it'd be nice to see this thing survive at least to what the Fluke 17V Plus does. Alright, again, let's just do a quick check. Should be, again, roughly 20 millivolts. Looks good. This will be 40. Again, this will be roughly 500 degrees Celsius. Leads are open. Looks fine. Let's try it with a 10 meg. Looks good. This will be 50 ohms. Looks good. This will be continuity test. Well, I've shut the beeper off, but it looks fine. And this will be a 0.1 microfarad capacitor. Looks good. And again, diode check mode. Looks fine. Alright, let me finish functional testing it. I gotta say, I'm pretty impressed. So our previous run, I did not perform the high voltage DC test, the AC rectified test, or either the ESD test. The very first transient I ran was this 1 kV 2 ohm source, 100 microsecond. The meter passed that, and then it failed at 1.5 kV with a 2 ohm source. So we have just passed 2.5 kV with this meter. So definitely a lot better. Of course, we have more to go with this transient generator. You can see we're still at 500 volts per division, still at 100 microseconds. And you can see we're now 6 divisions up, or 3000 volts. Again, the halfway point, 100 microsecond full width half height. Again, I'm not trying to repeat the IEC standards with these tests. I am just interested in how robust the meters are. And these are the waveforms that I've chosen to do that testing with. Alright, so here we go again. 3000 volts, 2 ohm source impedance, 5 transients, positive and negative, with each mode of the meter. And again, this is 2 times over what the previous meter had failed at. 17V Plus was by far the least robust of the Fluke meters that I've looked at so far. The beeper's quite annoying. Alright, that's it. Let's just see if it can read resistance. Look at that. I think it's going to end up being fine. Again, this will be a 10 meg ohm resistor. Dead on. This will be a 1K. Dead on. Here's a 50. Look at that. Oh, again, I got the beeper turned off, but again, this will be a 0.1 microfarad part. Looks good. Let's just try diode check. That's fine. And millivolts. And this will be roughly 40. Looks good. It's about 20. Let's try temp. 500. Looks good. And this will be roughly 5 volts. Looks fine. Let's try AC. This should be 2.5. Looks good. Alright, let me go ahead and finish functional testing it, but it looks like the meter's good. Alright, our Fluke 87V continues to hang in there. You can see we're at 1000 volts per division. I've kept it at 100 microseconds per division. You can see we're now 4 divisions up, or 4000 volts. It's looking really good. This spreadsheet isn't up to date by any means, but you can get an idea just how many meters had already failed by this point. At 2000 volts, the Klein Tools MM2000 had failed. The Unity UT61D had failed the piezo grill starter. The Amprobe AM530 had failed at 1.5 kV. The UT61E had failed the piezo grill starter. The Tech Power TP40 had failed at 1.5 kV. You know, there's a whole slew of them here, from Circuit Test, UTL, Southwire, Nova. Here's an X-Tech EX430. I mean, it's just a lot of them. Most meters don't make it up this high. So I'm glad that we ran another one. I'll tell you, Again, the only reason I ran this meter is because I had started a poll and quite a few people had asked to see a new one again. So here you go. Your meter is definitely holding in there. I'm impressed. I never thought the meter would survive even this far. So again, this will be 4,000 volts with a 100 microsecond full width half height and a 2 ohm source impedance. 5 transients, positive and negative. Sits right on the money. Alright, let's have a look again. This will be roughly 20 millivolts. Looks good. Let's try temp. Again, 500 degrees C. Looks fine. And resistance, I tell you, it looks good right now. There's 10 meg. Here's 50. Let's try it with a gig. Looks good. Continuity test works good. And this will be a 0.1 microfarad capacitor. Looks good. And diode check. Yeah, I'm going to say the meter's probably fine. I'll go ahead and finish functional testing it. I'll tell you, I'm very impressed. Even if this meter has a problem right now, I'm still impressed. 4 kV, this meter's just behaving completely different. Alright, so our Fluke 87V survived that test just fine. Again, we're at 1,000 volts per division, 100 microseconds. You can see we're now 5 divisions up, or 5,000 volts. It's like I have a completely different meter here. Unbelievable. Alright, 5 transients, 5 kV, 2 ohm source impedance, positive and negative, each mode. I'll tell you what it is. It's because it knows I have a bunch of Bob 199 sitting here. So at 5,000 volts, looks like the Hold Peak HP 760H had failed. The Unity 139C had failed. And the Keysight U1231A had failed. I'm not sure if there's others. Again, this is an old spreadsheet. Looks like only 9 meters had gone past this level though. Of course, some of those are modified, like the UT181A. Alright. You can see it's still reading the AC and DC voltages just fine. That's not where we had the problems with the original ones though. So again, this should be 20 millivolts. Looks good. Let's try temperature. Again, roughly 500. This will be a little over 1,000. And around room temperature. And again, leads open. No problems. Here's our 10 mega ohm resistor. Let's put it into high-res mode. Looks good. Again, let's try our 1 giga ohm. There you go, 1 nanosiemen. Let's try capacitance. So again, this will be a 0.1 microfarad. Looks fine. Diode check seems fine. Alright, let me functional test it the rest of the way. Alright. A little hard to believe, but our Fluke 87V is still just fine. You can see we're still at 1,000 volts per division, 100 microseconds per division. And now I have the Transient Generator turned up all the way. It's just shy of 6,000 volts. Again, the Fluke 17B Plus actually had survived this test along with every other Fluke that I tested. Originally, I would have never thought that this meter would have survived as far as it has, but that's why we run the test. So obviously there's a big difference between this meter and the last one I had looked at. So again, this is going to be just shy of 6,000 volts with a 100 microsecond full width half height and a 2 ohm source impedance, 5 transients, positive and negative, with each mode of the meter. Looking over our sheet, meters that have survived this test, there's not that many. The Bryman BM235 has. The Unity UT61E that I had modified past this test, it would never survive it the way it came from the factory. That's the same for the UT181 as well. The Hioki DT4252 survived this test. The Unity UT15C survived. Again, that's like a high voltage probe, it's not really a meter. The Fluke 115 survived. The Fluke 101 survived. The Fluke 17V Plus survived. The Bryman BM869S had survived. The Fluke 107 survived. And the Radio Shack model number or catalog number 2200087 also survived. Again, this list isn't the most recent, but there's just not that many meters that would survive off of this transient generator. This is a pretty big deal in my opinion. Certainly a huge difference between what I'd seen before and this meter. I can't tell you why. Obviously this is the latest of this meter. And obviously there are differences because it's functionally not quite the same. Let's just have a look again with the millivolts. This will be roughly 40. That looks good. Normally that would not work, and here's 500 degrees C. And this would not work. Normally you'd see some low resistance if we took out those diodes, and you could see there's 10 mega ohms. Let's just go ahead and put it into conductance. This will be again 1 giga ohm. Should read 1 nanosiemen, and of course it does. And let's go ahead and try capacitance. So again, this will be a 0.1 microfarad, and you can see it's spot on. Let's just go ahead and put it in diode mode. Again, I've got the beeper turned off, but there you go. I mean, here's a single diode, 0.6, looks good. So yeah, I'll go ahead and finish functional testing this, but I mean, all in all, I can tell you the meter looks real good. You can see I have our original transient generator out, and that's because the 87V survived that last round of testing. So to up the voltage, I have to use this transient generator. See, I have the high voltage probe out still, and again, they'll be looking straight across the meter. The generator is currently strapped for 6,000 volts. This generator has a 50 microsecond full width half height instead of a 100 microsecond, but it still uses a 2 ohm source impedance. Again, the energy level of this generator is fairly limited. It's also sub 20 joules. Again, we'll do 5 transients, both positive and negative in each mode, just like we did before, and then we'll functional test the meter. Let's just check real quick. Looks like everything's fine. Turn off the beeper. Okay, let's just check the resistance real quick. Looks like it's an open. Alright, I'll go ahead and functional test it. Alright, so the 87V checks out just fine. I've restrapped our generator for 8,000 volts. Again, this will be a 50 microsecond full width half height with a 2 ohm source impedance. Again, 5 transients, positive and negative. Alright, let's have a look again at the resistance mode. And again, it looks fine. Let's just try it with a 10 mega ohm resistor. Dead on. And let's just try the millivolts real quick. And this should be roughly 20. Spot on. Again, 500C. Looks good. Alright, let me go ahead and functional test it. I gotta say, when I woke up this morning, I thought I'm gonna run these tests today. I would have never expected it to go the way it has been so far. You know, this meter just continues to hold up, and I really, again, don't have an explanation for it. If we look at our previous data that I'd collected, we can see somewhere down here is the Fluke 87V Plus. And if we look across, right here's where this meter was finally damaged. This is 10,000 volts with a 2 ohm source and a 50 microsecond full width half height. That's actually the same level that I've got our generator set up for right now. Let me just show you what that looks like. Again, you can see we're at 2,000 volts per division and 20 microseconds per division. You can see we are 5 divisions up, or 10,000 volts. So if we go up about halfway and then go over, you can see we're real close to 50 microseconds, a little bit longer. So this is the transient that damaged the 87V Plus. I really have no idea how any of this is going to turn out at this point. I gave up guessing after we broke 3,000. Alright, here we go. That's what it looks like. Alright, that was 10,000 volts. Again, that was the level that the Fluke 87V Plus was damaged at. That, again, very impressive. What else can you say about it? Here you go, 10 mega ohms. Dead on. Here's a K. 50 ohms. Say 0.1 microfarad. We are in the millivolt range. Again, this will be 20 millivolts. And of course, that's going to be roughly 500 degrees Celsius. Here's our diode check mode. Let's see, volts. Well, here's 5 volts. Here's 2.5 and 2.5 here, and 60 hertz. Alright, I'll go ahead and finish functional testing it, but before we do that, got a little spark plug here. And all I'm going to do is attach our generator to this. And this is the transient I was just subjecting that Fluke to. Well, that's not much of a zap. Let me see if I can find a plug with a little bit bigger gap. Alright, so our 87V survived that test just fine. You can see we're still at 2,000 volts per division. And we are now 6 divisions up, or 12,000 volts. We're still at 20 microseconds per division. So again, we can see there's basically 2.5 divisions over, or roughly 50 microseconds. Alright, let's see if it'll go past this gap. Jeez. AGC, I'm sure, kicked in on that. Let's try it one more time. So again, this is going to be 12,000 volts with a 50 microsecond full width half height and a 2 ohm source impedance. Tested a few Flukes up this high. Let's just have a look. You can see I tested the Fluke 101 up here. I also tested the Fluke 115 here. It also passed. The Hioki DT4252, one of the plastic inserts, had already started to break down, and that occurred at 10 kV. So there was no electrical damage, just the plastic. I've run other meters up this high. Again, the sheet's kind of old, but certainly other Flukes have survived it. This is one big transient. Alright, let's see what happens. That's what it looks like. So far, no signs of a breakdown. Pretty nasty transients. Getting no sign of breaking down. There's the first one. And you can see no signs of breaking down. Okay. Just disconnect this. Get some of this out of the way. And this will be 2.5 volts AC. And this is with the blocking cap. Let's just try the frequency. You can see 60 Hertz. This should be 60. This should be 30, 15, 120. So that all seems fine. Should be roughly 70 volts AC. Yep, at 3.2 kilohertz. It's kind of odd. Oh, it's in manual range. I forgot about that. There we go, 70 volts. That looks fine. And this should be roughly 60. That's fine. Let's try it at 5 volts. There you go. In the millivolt range. And this should be roughly 40. Looks good. And this should be roughly 20. Looks good. And here's temperature, so roughly 500. Looks fine. Oh. There you have it. So we finally damaged the meter. 12,000 volts is what it took to do it. So not too bad. Again, that Fluke 17V Plus was damaged at 10,000 volts. So we exceeded that by 2,000 volts. Not too shabby. This should be a 0.1. It only reads 102. That's fine. Continuity test. That looks fine. Let's try it in diode check mode. So short. Let's just try it with a single diode. And here's 2 diodes. That looks fine. Here's our white LED. Oh, that's interesting. It's already changing. I wonder if it's a heat problem. We started out, we were at 4 meg. And now it's reading 10. Let's just try some different values. So this will be 1 ohm. This is a half ohm. Let's go ahead and zero this thing out. So here's our 0.5 ohm. 1 ohm. 50 ohms. 100 ohms, 1K ohm, 10K, 100K, 1 meg. Oh, you can see that? We're back down to 4 meg. Yeah, definitely something going on with it. So let's go ahead and pull it down and we'll have a look at it. Alright, so one thing I noticed when I took the meter apart, the shield had remained flat. This is the BM869S that Bryman had sent me. This meter has actually survived a 14,000 volt transient after I changed out the input protection transistors for a different one. So that meter is quite robust now. Alright, let's have a look. This should be 1.3 or so K. That's the PTC, that's fine. This is our 1K. That should be fine, yep. Make sure they're connected, that looks fine. This should be roughly 1 mega ohm. That looks fine. Let's see if this is leaking at all. I don't see any problem there. Let's look across our MOV. That looks fine. Let's check this one over here. That one seems fine. And this one here. That looks fine as well. At least they're not leaking too much. Let Let me just flip this around. So let's check our TVS. Again, this should be 0.7. And it is. Let's have a look at it this way. It should be an open. That's fine. Let me just scooch the camera in here a little closer if I can. Alright, so should be roughly 1.3. Yep. Here to here. It should be 0.7. That's right. And here to here, 0.7, that one's good. And here to here, yep, 0.7. And here to here, yep, that's 0.7. And here to here, that's 0.7. And here to here, that's 0.7 and 1.3 as well. So I don't see anything wrong with our input diodes. It all looks good. Alright, you can see I removed the MOVs. That's not where our leakage is. So I'm back to thinking it's one of the diodes. What I'm going to do is just go ahead and remove these. We'll just take them all off right now. There you go. So it's not the MOVs, it's one of these diodes. It's just leaking ever so slightly. So I can't detect it with a meter. When I look at them all, they all look fine. They've all been stressed. There's no reason not to replace them. I've got brand new ones sitting here for it anyway. Alright, so all I've done is put the MOVs back in. So I just want to make sure that those aren't leaking before we go ahead and add anything else to the mix here. So let's just attach a couple of quick leads, and I'll leave those open for now. Let's set this to ohms. Hey, and there you go. So it's open circuited. So this is with the MOVs in place right now. And here we are with a short. No problem. You can see I've gone ahead and installed the new diodes. These meters have to be cleaned quite well. Be very careful when you work on these meters. You got to make sure that things are kept very clean. I said that numerous times. You can't make it too clean, that's for sure. Let's get our contacts cleaned up. And I think we're good to go. I'll tell you, it's been a long day. I'm afraid that the reality is they're just not putting the shield inside of the slits like that, because it definitely fits very nicely. At least I'm not seeing any kind of problems with it. Again, you can see it just fits very nice and flat. And we won't put the screws in this just yet. Let's just make sure it does anything. So let's see. Put the battery in. Let's see if it fires up. Alright. We got our Fluke 87. I'll on startup. That's a good sign. Let me clean up some of the bench. Let's get our soldering iron out of here. Let's just see. So that should read 0. This is an AC coupled 2.5 volt. That's normal. This is DC coupled 2.5. Let's just look at the frequency. That's fine. Again, this should be roughly 70 volts at 3 kilohertz. That's fine. That's fine. Again, it goes into manual range. Here we go. So about 70 volts. Let's try DC. Again, this should be about 60. That looks real good. And this should be 5 volts. This should be 2.5. This should be 0. That looks fine. And let's see, this should be roughly 20 millivolts and 500 degrees Celsius. That looks fine. Alright, so let's just try continuity real quick. That looks fine. And capacitance mode. Let's go ahead and roll this out. Might be a little tougher sitting on the bench the way I've got it. So this is 150 picofarads. That looks fine. This is 1 nanofarad. Looks good. Alright, so again 0.1 microfarads. It's interesting how the auto range works. Let's just try some of the other capacitors. So this would be a 1 microfarad. And this is with a 10 microfarad. And this is our 100 microfarad. Looks good. And let's try resistance. Again, this is with the lead shorted. Let's just go ahead and rail that out. So again, 0.5. And this is with a 1 ohm. This will be our 50 ohm. And 100 ohms. Let's take it out of rel. This will be 1K, 10K, 100K, 1 meg, and 10 meg. Looks good. And again, let's go to conductance mode. This will be our 1 giga ohm resistor, and that should read 1 nanosiemen. Looks real good. Let's just try it with our 100 meg. Again, this should read 10 nanosiemens. Dead on. And this will be our 40 meg or 25 nanosiemens. Looks real good. Try it in current real quick. Again, I haven't done anything with this mode. Change the mode. So there's 100 microamps, 10, 1, and 100 nanoamps. Alright, so the meter looks just fine. So again, the MOV's undamaged, but we did damage some BOV 199s. They started to leak. On the previous test, when I took out the 199s, it actually cracked the cases. And that was at a much lower voltage, so yeah, definitely something has changed about this meter, that now all of a sudden we've gone from cracking diodes to just getting them to leak a bit at a much higher voltage. So I'm pretty pleased with that. I'll go ahead and finish putting the meter back together. All right, there's another thing we should probably check real quick. Let's just have a look at our input impedance now. So again, this should normally read about 10 meg. That looks fine. Now let's try it in our high Z mode. Yep, you can see it just over ranges. Yeah, so that seems fine. Again, if we take it back out, it should go back to 10 meg. Yep, looks good. Alright, so before I say goodbye for this video, I thought I'd show you the next test that I'm planning on running. So this test setup that you're looking at is for part 6. So you have a couple of meters out. This little tablet is running the software that I wrote for my motorcycle data logging system. And this is talking to this small lab jack. This is just a generic data logger. And I'm just using the 2 analog inputs of this, and that's what's being plotted here. This is just a standard DC power supply. That high voltage supply is currently connected to a 10 mega ohm resistor. So this Brahmin is looking at the voltage across our 10 mega ohm resistor, but it's a divide by 10 because I'm going through this small attenuator. Now what I'm going to do is go ahead and increase the voltage. Try to get this to 1,000 volts. It's pretty close right there. Alright, so this power supply is capable of putting out 5,000 volts. On the monitor outputs, those are both 0 to 5 volts. So in this case, 1 volt would equate to 1,000 volts. So again, if I raise and lower that voltage, you can see it goes up. So let's just go ahead and we'll set it roughly 2,000 volts on our graph. That's pretty close. Oh, excuse me, that's 1.5 kilovolts. And we can see in our Brahmin here, we're reading 1.5 kilovolts. So the other output is the current. And of course you're wondering why 1.5 kV is putting out that much current. First of all, this attenuator is going to absorb quite a bit of current as well. So let's go ahead and we'll detach that. And you can see the current came down right away. What I'm going to do is adjust the power supply back to 1,000 volts, just to keep our math simple. And there you have it, so roughly 1,000 volts. And this is displaying somewhere around 2.5 volts now. And that's because this power supply's current limit is 200 microamps. 200 microamps would be full scale or 5 volts, so 2.5 volts would be half of that, or 100 microamps, which is exactly how much current we're putting through that resistor right now. So with this data logging software, I can change how fast I want to record, and I can also record it to the disk drive and bring it up in a CSV file for later, and then we can go ahead and plot it. But we should be able to see right on the screen over time any kind of long-term trend. Alright, so what's the point of this whole test? Well, somebody had written me that if we put in a DC voltage into the input jacks, and worst case around 1.2 kV, that would damage the input MOVs. So I had offered to run this test on this particular meter, so let's go ahead and put that into the test jig instead of our 10 meg resistor. This trace here is our output voltage, so roughly 1.2 kV. It's just a little over that actually. And this is the current again that's going through the MOVs. Again, on these meters, the MOVs are not switchable, so they really have nothing to do with a function switch. However, if we turn on the meter, that should change the current quite a bit. There you go. Alright, so what I'm going to do now is just let this thing set for about a week. What we'll do is we'll see if the MOVs degrade over this period of time. What we would expect to see if they were degrading is the current should eventually go up. Alright, well, that's going to be it for this video. Hope you enjoyed part 5. In part 6, we'll review the data that we've collected for this, and we'll also probably do our switch cycling. So I'll see you in part 6. Later.